You'll have noticed by now that actually constructing the approximate confidence interval is rather easy. You start at what you've seen in your sample and you give yourself a couple of standard errors of wiggle room on either side, and you've got an interval that you can use to estimate the number that you're trying to get at in the population. But there's a little subtlety associated with it, which is the disappearance of the word chance and the new word confidence, and it's worth taking a look at that for a few seconds, even though you might not want to dwell on it for a long time. And so for this, I'd like you to imagine a population whose average happens to be 3.5. So just the box of tickets that represents the 6 numbers on a die, if you like. And so supposing you're trying to estimate a population mean, and Taiki already knows it's 3.5, but of course you don't, because you only have a sample. This is the typical scenario. And so you take your sample and you go through your calculation process that we've developed, and you get a confidence interval that goes from 3.42 to 3.51. So what is that confidence interval doing? It is allowing you to say that you think that this population mean is in the range 3.42 to 3.51. Now, Taiki happens to know that it's 3.5, so she will know that it's a good interval. It's what in your picture that you drew the section before would be a green interval in that picture of good intervals and bad intervals from your textbook. And what you have to observe is the obvious fact that this interval 3.42 to 3.51 has both its endpoints fixed. 3.42 is not moving about on the number line, and nor is 3.51. The unknown mean 3.5 is also not moving about on the number line. Taiki can actually see it, you can't, but both you and Taiki know that it's not moving about on the number line. It is a fixed number. And so that number happens to be in this interval, and it's always in that interval. There is going to be no occasion in which this fixed 3.5 is not in this fixed 3.42 to this fixed 3.51. And if instead your sample had produced a confidence interval that went from 3.38 to 3.49, well, this would be a bad interval. It would be colored red in your picture that you were drawing the section before. And it never contains 3.5. And why am I making such a big deal about this obvious fact? It is because for neither of these intervals can you say there's 95% chance that it contains 3.5. The chance is either 100% or 0%. The situation is this: before you've tossed the coin, there's a chance half that it lands heads. But once you have tossed it, the chance that that particular toss that is over is a head is either 100% or 0%. Now, you might know whether it's 100% or 0% depending on whether you can see it. But even I, who can't see your coin, know that it's a 100% or 0% because that coin is not going to change its face. It has already landed. And this is a significant frequentist interpretation of what is going on. And so the important thing to note is after the sample is drawn, the confidence interval is fixed. The two endpoints are just two fixed numbers on the real line. They either always contain the fixed population mean or never, and it doesn't matter whether you know it or not. What matters is that the population mean is considered fixed. It's not something on Mondays, Wednesdays, and Fridays and something else on Tuesdays and Thursdays. It's just a single number. And so the confidence is not so much in the interval. When I look at a confidence interval, I actually don't have any idea whether that contains the population mean or not. The confidence is in the procedure which generates a good interval about 95% of the time. And what do I mean by 95% of the time? If you look at all possible samples that you could draw, from each sample you'd get perhaps slightly different interval, and 95% of those intervals would be green intervals. They would contain the population mean that you're trying to get at. And so the confidence is not so much in the interval as in the procedure that generates it. And this is something that you have to start getting used to in anything, any decision-making process that is based on random samples, in the long run, they give you good answers a very high percentage of the time. In any particular instance, you could be wrong. So what I want to do now is I want to look very hard at the numbers and what each ingredient in the calculation means and does not mean, and what's normal and what's not normal. And we will do it by means of a sample of incomes. So I've got a simple random sample of 400 households taken in a large area. You're allowed to assume that the population is so large that there are no correction factors involved, just as we've been doing throughout. And I'm looking at annual household income as my variable, and I'm interested in the average annual household income in the large area. But unfortunately, I don't have the resources to go to every household in the area and find out what the income is, and so I have a sample, which is a simple random sample, and this is critical because the simple random sample, not just any old random sample, allows us to use the formulae that we have developed in this class to make estimates. And the sample is something that I can completely see. So here is how the sample came out. It's a simple random sample of 400 incomes. It should come as no surprise to you that the histogram has a right-hand tail. Distributions of incomes are frequently like that. It happens that the sample average was 61.6 and the sample SD is 39.5, about 40. No surprise there that the distribution is not normal, that it has a right-hand tail. What I've done here is I've marked the balance point, the average of this distribution, and I've gone 1 SD on either side. So basically this is 60 plus or minus 40 roughly, and so this is, from 20 to 100. And that I can completely see. But I want to use this sample for something. I want to use the sample to guess the mean annual household income in the entire area. So if I had to guess a single number, what would I guess? Yes, I would guess the number that I saw in the sample, 61,650. But I have to give myself wiggle room. Now, why do I have to give myself wiggle room? I've said it before and I'll say it again, because my sample could have come out differently. And so I have to imagine all the different ways the sample could have come out, and I have a nice little calculation that tells me, well, first let's do the calculation. You have your sample SD, which is used as an approximation to the population SD, divided by square root of the number of draws, and that gives you a number that's just under 2,000. And what is that? That measures the rough difference between this sample mean and the unknown population mean. And this allows us to construct our confidence interval for the population mean. We're saying the population mean is in the range sample mean plus or minus a couple of standard errors, so 57.7 to 65.6, and we're saying that with 95% confidence in the procedure that generates this interval. In brief now, we think that the population mean is in this range. And I want to take a look at what went into it. What went into it is the sample mean, the standard error for the sample mean, and this 2, which comes from where? 95% confidence, yes, and the normal curve. That center plus or minus 2 measures of spread contains 95% of the area. That is a fact about the normal curve, and not this curve necessarily. So where exactly is the normal curve that is being used? It's not this one. What's this roughly 2,000? Because I don't see a 2,000 on this picture. So for a little while, we're just going to look at this picture again and the other picture that we can't see, but Taiki can. And so starting again with the picture that we can see everything there is to be seen about the sample. We have a list of all 400 numbers. We can draw its histogram. We've got its average. We've got its SD. And what Taiki can see, and I'm going to be less fanciful and say what the Census Bureau would see, because if the Census Bureau has the means to go to every single household in the population, the Census Bureau would see this. This happens to be the population from which this sample was drawn. Lots and lots of data points, lots and lots of households in the sample. There were hundreds of thousands of them, as I recall. And an income distribution, no surprise, and also no surprise that your distribution of 400 randomly sampled incomes kind of looks like this one. Its mean is 6165, this mean is 60. Its SD, the sample, is 39.5, the population SD is 40. These numbers are all very close to the corresponding numbers in the sample. The distribution of the population is kind of sort of the distribution in the sample, and this is visually the representation of your large random sample looking like the population. Not exactly like, of course, but kind of sort of. And so let's recall the calculation that we did that said that the approximate standard error for the sample average was, well, the actual standard error would have been the population SD divided by square root of sample size. What we have, because we cannot see this, you can put your hand over it now if you want. We have this 39.5 standing in for 40. So we use the 39.5 over root 400 and we have just under 2000 as our standard error for the sample average. And what is that measuring? That's not measuring spread inside the sample distribution or spread inside the population distribution. It's measuring a distance between two numbers. It's measuring a distance between this population mean and this sample mean in the generic sample mean. You expect the sample mean to be within a couple of thousand, maybe within 4,000, maybe within 6,000 of the 60,000 population mean. That's what this is saying. And what, in your case, what sample mean did you get? You got 6165. And that's 1650 away from the population mean. That is less than one standard error away from what you are predicting. So you got a sample that's pretty close. It could have been further away. And you used this to make an estimate for this 60,000, which of course you don't know. And you're saying that that number is in the range 57.7 to 65.6, is it? Yeah, it happens to be. So you got a good interval. With this sample, you got a good interval. Now put your hand over this part again and notice that all you can see is the sample and the calculation here. And this picture is of what the census would see if we had the resources to get everybody, is a sort of reassurance of what is going on and a reminder of what the standard error for the sample average is measuring. What is not reassuring at all is, of course, there's no normal curve in sight. The only place where the normal curve pops up is in this calculation, where two standard errors we're saying lead to 95% confidence. Well, where is that normal curve coming from? Because it is certainly not the distribution of incomes in the sample, and it is certainly not the distribution of incomes in the population. What is it? And here we come back to why is there an interval at all? There is an interval because you have just one sample, and the sample could have come out differently. So you have to imagine all other possible samples, what their averages could have been, and what those probabilities are. And it's the central limit theorem that tells you that those probabilities are normal. From a more practical perspective, if you imagine all possible samples, then every one of those has an average. How many samples are there, by the way? You're choosing a sample of size 400 from a population of several hundreds of thousands, right? So supposing it was 300,000 in your population, then the number of different samples you could pick is 300,000 choose 400, which is a massive, great number. That's a lot of samples that you could pick. And they'd all have their own average. And that would be a long list of sample averages that you could get. And if you draw the histogram of that long list, then that histogram of all the means is normal by the central limit theorem. You see each different sample mean along with the proportion of times that it could possibly appear. Now I actually drew that thing. And I did not want to have my computer smoke by drawing all possible samples, so I drew lots and lots of samples. I drew 20,000 samples of size 400 each from the population. And so I had a list of 20,000 sample means, and I drew the histogram of those 20,000 numbers, and look, what shape is that? Yep, it's roughly normal. Where is it centered? 60. No big surprise. The center of that distribution is at the population mean. You expect the sample mean to be the population mean, give or take. Where are the points of inflection of the curve? At 58 and 62. 2 away from 60. This is in thousands of dollars. 60,000, give or take, 2,000 roughly. That's your standard error for the sample average. Your single sample average that you got is one of these guys. And what you're saying is that the generic sample average is a small multiple of $2,000 away from the population average. That's what you're using to estimate your population mean. And the normal curve that has been drawn is not a data histogram. It's not the histogram of the data in the sample. It's not the histogram of the data in the population. It is the histogram of all possible sample means drawn from all possible samples. Equivalently, all possible sample averages and all of their probabilities. And that is something that takes a while to get one's mind around, because you have the one sample, but somewhere back there you and the mathematics between you are imagining all other possible samples. That's a lot to imagine. But every time you make a decision based on a random sample, that is something that you have to do. You have to imagine the other ways that the sample could have come out. Otherwise, you won't be able to get a sensible measure of how far off you can be. And that's really the main story of what all the numbers mean. What I want to do is I want to take you now through a couple of short observations. One is something now related that you will read in newspaper articles, and you should know what you're reading. And I'll start with that. And that statement you see sometimes in newspaper articles in the United States about surveys. So you have a newspaper article about a survey, somebody's taken a survey before an election, and the first thing they'll give you is one headline. Proposition A, too close to call, 49% are going to vote for it. That's going to be the headline. And then your next paragraph is going to have some percent for Proposition A, some percent for candidate X, some percent for measure, etc., 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 etc. Lots of estimates based on a single sample. And you as statisticians will look at that and you will notice a couple of things missing. You will notice the big thing missing is any measure of error. Right? So you think 62% will vote for candidate X, 62% plus or minus what, sorry? Well, the plus or minus isn't going to be up there. And nor is the sample size. Because why? Because that's too much technicality for people browsing the internet or reading the newspaper along with their breakfast. That comes way at the end. If you are patient, and if you read all the way down to the end of the article, you may see a sentence that looks like this. The margin of error in such surveys is about 3 percentage points. Now, I just took 3 as an example. It could be 2 or 4 or whatever. And here is where you have some sense of what the errors are, and I want you to understand what this number means. Essentially what's happened is somebody's made a confidence interval. Right? There's an estimate plus or minus a few standard errors, and those few standard errors add up to about 3%. So center plus or minus about 3% is their interval. How many standard errors depends on the level of confidence that the survey is using. Typically it's 95% confidence, but I'm not going to swear that everybody uses the same level of confidence. So it could be 2, could be somewhat more than 2, very rarely 3, depending on the level of confidence they're using. This 3%, which is essentially, you're supposed to think of it as the width of the interval from the center to the edge, so that the whole interval is about 6% long. That 3% is typically not 3%. It might be 2.84%, but nobody wants decimal points with their morning coffee, and so they'll get about 3% is what they're told. And moreover, notice all these different proportions. If you use the bootstrap method, then your SD used in calculating the standard error would be, you would use square root 0.49 times 0.51 here in the numerator, here 0.62 times 0.38, etc., etc., etc. And those would all be different. What's typically done is you've used a conservative measure, and typically 0.5 instead of the observed proportions. You by now understand very well why 0.5 would be used to give you the widest possible interval. And so somebody has constructed conservatively confidence intervals, and the distance from the center of the interval, the estimate, to the edge of the interval is around 3% in this example. So if it was 4 percentage points, that would be around 4%. And that's the technicality. But what does it actually mean? Imagine somebody who doesn't have a statistics course reading this. The margin of errors in such surveys is about 3 percentage points. They can be forgiven for thinking that 23% are undecided about this measure. And, well, maybe it's not exactly 23%, but it's somewhere in the range 20% to 26%. It sure looks like that's what this sentence is saying. 23% plus or minus 3%. I'll get it right to within that. And you know that, yeah, well, kinda. What you know to be true is that for such surveys, most of the estimates are going to be correct to within 3% or so. That is to say that most of the intervals that you draw are going to be green for their respective parameters, but there are always some red ones. And you as statisticians must keep in mind that sometimes you're going to be off by more than that 3%. Sometimes your interval is going to be red. It's going to be off your true value entirely. And these words of caution don't appear in the newspaper, but you need to have them in your head. Yeah, most of the time, and if you're drawing 95% intervals, then about 95% of the time your error is within 3 percentage points, perhaps. But 5% of the time it's more. And so please be aware that any decision made based on a random sample is subject to errors, and you can quantify the proportion of times you're going to be off. Now I will leave you with a final thought about estimation. And I'm going to do a calculation that's very commonly done. So here are my data. I have a Stat2 class with 300 students, and they take a final exam, and their average score on the final is 65, and the SD is 12. Right, so I have a list of 300 scores. I've calculated its average, and I've calculated its SD in the way that you have been used to doing all along. And so, ta-ta-da, I do a calculation that I now know how to do. I take an SD and I divide by square root of the size of my list, and I've got 12 over root 300, which is close enough to 0.7, 0.69 something as I recall. And so, well, I now know how to calculate, and so I do mean plus or minus a couple of these things that I've calculated that look awfully like standard errors. And that's an interval. 65 plus or minus 1.4. And so that looks like a confidence interval. What is it a confidence interval for? So we go back to something we said a couple of lectures ago. When you see an approximate 95% confidence interval, jargon, language, you take all of that and you replace it by one word. And what is that word? This thing is an estimate of what? Well, let's see. Is it the average final score in this class? No, the average final score in the class is just 65. I know it already. I don't have to estimate that. Certainly not by any interval. That is just 65. So then what am I estimating? My technique says I'm estimating the average of some population from which my sample is drawn. So these 300 students are a sample from where? From all students in Berkeley? Well, I can certainly think of them as a sample from all students in Berkeley. Is it a probability sample of all students in Berkeley? Well, you're not at Berkeley, but I am. It is not. Students sign up for courses. Students are not selected by throwing the entire population's names into a hat and then selecting at random. So these people aren't a random sample from anywhere. As far as I can see, there's nothing sensible to estimate here. So as far as I'm concerned, this calculation that I've done looks very much like calculations that we've done before, but under the circumstances, it yields a confidence interval for nothing. You're not estimating anything here. Nothing is random. If you wish, you can concoct a story. You can say, well, I'm going to imagine these 300 students as a simple random sample from where? Well, maybe from some imaginary population that has over the years taken Stat2. You know what? You can make up a story. And if you believe that story, that these 300 students are like a simple random sample from that population, and if you are interested in the mean of that population, then yes, this thing is a 95% confidence interval for that mean. But you better believe in your story. If you are going to apply our techniques in situations where there are no random samples, you better have very clear assumptions about the probability model. Now, sometimes these assumptions are justifiable. The classic situation is when your data are repeated measurements made on a certain object, scientific measurements. Over and over again, you measure the same thing. This happens a lot. Those measurements often do look like random samples drawn from a population, and then these intervals can be used as confidence intervals for the unknown measurement that you're trying to get at. But my Stat2 class, I really don't know. If you're going to make a probabilistic model for it, make sure it's clear. Make sure that the numbers, in fact, are like a simple random sample from a population, and that you're interested in the mean, and only then use these calculations. And when in doubt, if you don't have a model that you can believe, just follow a simple rule. Yes, you've learned how to calculate, but just because you can calculate doesn't mean you should calculate. Don't waste your time. And don't waste the time of others by calculating things that don't make sense. And on that cheery note, we're going to end our discussion of estimation. And next time, we're going to move on to another way of doing statistical inference, which is called testing statistical hypotheses.